Hello everyone, we are at the topic of CMOS transistors, and today we are going to look at the transfer function of an example CMOS circuit. We are going to use this circuit problem to find the transfer function of this CMOS circuit. So the question is, in the below circuit, find VI, the input voltage, and ID, these two currents, when both NMOS and PMOS transistors are in saturation. What is the range of Vout in this case? These are the parameters of the transistors. Here is our circuit. I wrote the KCL at the output node, at this node, because nothing is connected to the output of this circuit. ID1 and ID2 are equal, and this is source to gate voltage of transistor 2, which is a PMOS transistor, and this is the gate to source voltage of transistor 1, which is an NMOS transistor. So I wrote 2 KVL, one for the top loop and one for the bottom loop, and from the bottom one, VI is equal to VGS1, and from the top loop, VSG2 equals to 5 volts minus VI. Let's first find the range of VI for which Q1 and Q2 are off, because we want to find the complete transfer function for this circuit. When Q1 is off, we know that VGS1 is less than threshold voltage of transistor 1 and ID1 is equal to 0. I also know that VGS1 is equal to V1. From there, VI is less than 1 volt. So for these VI values, Q1 is going to be off. Let's check the status of Q2. I know that ID1 and ID2 are equal to 0 because one of them is 0, the other one is also equal to 0. I also have this KVL here. VSG2 is equal to 5 minus VI. From there, because VI is less than 1 volt, VSG2 is greater than 4 volts. So I need to check if Q2 is on or not. Because VSG2 is greater than 4 volts, if it is greater than 4 volts, it's definitely greater than 1 volt. Previously, we saw that when a MOSFET is on and its drain current is equal to 0, that means VSD of that transistor, drain to source voltage of that transistor, is equal to 0, and MOSFET operates in the triad mode. For these VI values, Q1 is off and Q2 is in the triad mode. From this loop, I can write plus minus VSD of transistor 2. Vout, if I write a KVL in here, Vout is equal to 5 volts minus VSD2, and because VSD2 is equal to 0, I have 5 volts for Vout. The below graph shows part of my transfer function for this CMOS circuit. I'm going to solve the rest of the circuit to complete this graph. Now we would like to find out for what values of VI Q2 is going to be off, what is the state of Q1 in that case, and what is the value of the output. When Q2 is off, VSG2 is less than absolute value of the threshold voltage of the PMOS transistor. Also, I know that ID2 is equal to 0. The value of threshold voltage is 1 volt, and I have this KVL, which I found previously. I'm going to use that to find the range of VI. So for VI values greater than 4 volt, PMOS is going to be turned off. I know that the drain current of PMOS and NMOS are equal, and when ID2 is 0, ID1 is also going to be 0. Also, I have this KVL, VGS1 is equal to VI. When VI is greater than 4 volts, that means VGS1 is also greater than 4 volts, which means VGS1 is greater than threshold voltage of the NMOS transistor, which means that VGS1 is already greater than 1 volt. As a result, Q1 is on. Just like before, Q1 is on with a 0 drain current. That means VDS1 is equal to 0 and Q1 is in the triad mode. For VI values greater than 4 volt, Q2 is going to be off and Q1 is in the triad region. And the value of Vout is equal to 0. So we are at this region. We completed one more part of this transfer function. Moving on, we want to study the case of both transistors operating in the saturation region. Here are the drain current equations for MOSFETs operating in the saturation region, and the condition of the drain source voltage for both PMOS and NMOS when they are operating in the saturation region. V overdrive of NMOS is VGS minus V threshold of NMOS, and that's equal to VI minus 1 volt. V overdrive of PMOS equals to VSG of PMOS minus absolute value of V threshold for PMOS, and that is equal to 4 minus VI. Now, because ID1 and ID2 are equal, and I know the equation of ID1 and ID2, if I equate these two, that's going to give me the value of VI, and I can use it to find ID. So if you solve this equation, VI is 2.5 volts, and the drain current for both of them is 1.125 milliamps. Now I want to find the range of V out for which Q1 and Q2 are in saturation. When Q1 is in saturation, VDS1 is greater than V overdrive, and V overdrive of NMOS we already calculated. It's VGS1 minus V threshold of NMOS, and now I have a value for VI. From there I can find the value of V overdrive for NMOS, and I'm going to use it to find the range of VDS1. So VDS1 is going to be greater than 1.5 volt. And because V out is equal to VDS1, this is VDS1. And I can use this KVL to find V out. This is VDS1. So V out is equal to VDS1. From there, I see that when Q1 is in saturation, V out is greater than 1.5 volt. Let's continue and check Q2. We want both Q1 and Q2 to be in the saturation region. For Q2, when it operates in the saturation region, VSD of 2 is greater than V overdrive of PMOS. I use the VI value to calculate the V overdrive of PMOS. It's equal to 1.5 volts. So VSD2 should be greater than 1.5 volts. And I need to find the relationship between V out and VSD of transistor 2, which I can find it by using this KVL in the following group. That's going to give me V out is equal to 5 volts minus VSD of transistor 2, and from there I know that when Q2 is in saturation, V out is less than 3.5 volts. So for VI equals to 2.5 volts, Q1 and Q2 both are in saturation, and the range of V out is between 1.5 volt and 3.5 volts. So I added one more piece to my transfer function graph. The new region is here. In this region, Q1 and Q2 are both in saturation. This graph shows the complete transfer function for that CMOS circuit. We added this portion and this portion to the previous graph. For VI values between 1 and 2.5 volt, for these VI values, the output is going to be between 3.5 volts to 5 volts, and the output is this voltage here, VDS1. So VDS1 is a large value greater than overdrive voltage of transistor 1. As a result, Q1 is in saturation in this range. From this 5 volts, most of it is going to drop across drain to source of Q1, and the smaller portion of this 5 volts is going to go for VSD of transistor 2. As a result, Q2 is going to be in the triad region. For the case of VI between 2.5 to 4 volts in this range, V out is changing between 1.5 volt to 0 volts, and this V out values, which is the same as VDS1, are considered small values, and they are less than overdrive voltage for Q1. As a result, Q1 is in the triad region, and source to drain voltage of Q2 is going to have larger value than V overdrive of transistor 2. As a result, transistor 2 is going to be in the saturation region. So this is this region, and this is this region. This is the summary of the transfer function for this CMOS circuit. For VI values between 0 and 1 volt, NMOS is off and PMOS is in triad region. For VI values between 1 and 2.5 volts, NMOS is in saturation, PMOS is in triad region. For VI equal to 2.5 volt, both of the transistors are in saturation. Then VI increases between 2.5 volts to 4 volts, NMOS is in triad region, and PMOS goes to saturation. And for large values of VI between 4 and 5 volts, NMOS is in triad and the PMOS is going to be off. And the graph on the right, this one shows the ID current for this CMOS circuit. When VI is less than threshold voltage of NMOS, because ID1 is 0, ID2 is also 0, so I is equal to 0. In this range, there is no current flowing in the circuit. And when VI is greater than VDD minus threshold voltage of PMOS, ID2 is going to be equal to 0 because Q2 is going to turn on. When both of them are in the saturation mode, the highest current is going to flow from drain to source of these transistors, and this is the maximum current in this circuit, which happens when VI is equal to half of VDD. This graph for VI is symmetric because the parameters of Q1 and Q2 are equal, or they are matched. VTN is equal to absolute value of VTP, and Kn for Q1 is equal to Kp for Q2. As a result, it's going to be a symmetric graph. So transfer function is also symmetric for matched transistors, and in stable state the current is equal to 0, but during the transition from one state to another state, or from one mode of operation to another mode of operation, ID is going to be a non-zero value. Please note that in this circuit there is nothing connected to the output of the CMOS transistors. For our transfer function, VDD was equal to 5 volts, so we used VDD of 5 volts in our example, and VTP, absolute value of VTP, was equal to VTN, that was equal to 1 volt. So it's 1 volt, 4 volts here, 5 volts here, and 2.5 volts in here. We already calculated the value of I peak, and that was equal to 1.125 milliamps for our example circuit. In summary, we found the transfer function of an example CMOS circuit and calculated the maximum drain current in the circuit. Thank you for watching.